Hi everyone. For my final project, I wanted to see if I could optimize sparse matrices by using hash maps instead of ordered linked lists. Sparse matrices are a very cool concept to me, but it is also very useful in computer science. Sparse matrices are super useful in many areas because they let you work with data that's mostly zeros without wasting space or time. In machine learning and data science, they're great for things like text analysis and recommender systems, where most items don't get interacted with. They also pop up a lot in engineering and scientific computing, like solving equations in simulations or representing networks as graphs. Plus, they're handy in image compression, feature extraction, and even bioinformatics. By saving memory and speeding up calculations, sparse matrices make it easier to tackle really big problems efficiently. Matrix multiplication is also essential to the neural networks that AI use. This is the old code for sparse matrix from assignment 2. Uh, Here is, see, we are using ordered linked lists. As a reminder, the sparse matrix is just a list of ordered linked lists. And I remember for the next assignment, we did performance testing for matrix multiplication, and my sparse matrix was actually running slower than the mol-mat, uh, the, the normal matrix multiplication. Even though the sparse matrix was holding a much smaller amount of values, something was slowing it down to the point that it was getting beat by a dense matrix. I believe it was because we were using linked lists. So now I'll go through the performance testing for that part real quick to show you. So this is for MolMat. We'll just go to 500. So for a 500 by 500 matrix multiplied by another, it takes about 6.65 seconds. And for the sparse matrix, it takes a bit longer. So 8.7 seconds. And I believe the reason it's slower is because each access of a linked list is O of n, since it has to traverse through each element to get to the element that you want. So if you look at the mat-mul method, we can see how many accesses we have to do. And remember, each of these is adding another O(n). Here, on top of the three for loops, we have to set, it's another traversal, and then we have to get, it's another traversal, and then we have to get from the other matrix, which is a third traversal. So I remember back in week 3 having a discussion with Professor Yang where I was telling him how I was so confused why my sparse matrix was performing slower than normal matrix multiplication. Even with matrices with 1% density, normal matrix multiplication was faster. It was only until I dropped the density to 0.1% that sparse matrix finally showed its advantage. Professor told me to think about the data structure that we used. Linked lists are slow because each access has to traverse through the list. He told me that we would soon learn how to implement dictionaries, and accessing an element in the dictionary doesn't require any traversal. At the time, this kind of blew my mind. But soon we would learn about hashing, and I realized that this could be a much faster data structure to use in a sparse matrix. Each access in a hash map is O1. On the left here, we can see this is my implementation of sparse matrix using hash maps. So on the right is the old one, so we can compare. On the left here, instead of using an ordered linked list, it was pretty easy. I just switched this over for a hash map. And because hash map, we implemented the get item and set item methods, the dunder methods, we could basically, I did not have to go into the internal code of hash map at all. I could just use it essentially as a dictionary. So this is my get method, and here is the row. This row is basically a dict, and then using the column index we use at the key, and then from the dictionary, the key, we get the value. Here we have my set method, and I had to make a few more changes to the set method, and this is actually much simpler using the hash map because in the old method, if I wanted to say update a existing cell, I would first check uh, if it already existed, and then I would update it using this part. But using a dict kind of syntax, uh, we can just take the dictionary and index it by key, and whether this key exists or not doesn't matter. If it already exists, we just update it, the value to the new value. If it doesn't exist, we just create a new key value pair. Here is my mat_mul method, and the logic is exactly the same as the old one, except you have to change the syntax because it is now basically a dict. So right here, this is dict access syntax. So at first, my mat_mul function for the new sparse matrix was taking an extremely long amount of time, and there were two key fixes or two key problems in my code that were causing this unbelievably high number. The first thing was that I had copied it over from my old sparse matrix, and there was this unnecessary step that I did, which was this remove. I would remove when updating. Basically, if I was trying to update the value of an existing cell, I would first remove it. And in the new implementation, this is unnecessary because this line takes care of it. So after fixing that, these are the numbers. It's much better, right? 500 or 450 seconds to 24 seconds. But it was still slower than mat_mul with linked lists. So I looked for any other problems. And another thing I wasn't doing at that time was checking whether the value inputted was the default value. So when I was running performance testing, it would input a very large an array which is mostly zeros. And it would put all in, this is the line that prevents the zeros from coming in. So I was basically working with a dense matrix where all the zeros are being put into the sparse matrix, but this line prevents it. And after adding this line, here are my performance. So after adding that line, here are my performance figures. This side is when I still had the remove function and I didn't check whether the new value was a default value. And then here is after all the fixes. Much, much faster. So without this line, the sparse matrix is basically acting like a dense matrix where all the values, even if they're zeros, are being calculated for. So even after making all the fixes to set and the rest of the sparse matrix with hash map, I was still getting longer times than the sparse matrix with the ordered linked list. And this troubled me for a very long time, and I couldn't figure it out. But then I realized that I was testing using 0.1% density still. So it's a very small density. And the sparse matrix often have very few non-zero entries per row. If each row typically has only a handful of keys, the ON traversal in a linked list is effectively O1 for small number. So I realized the issue was that I was still testing using 0.1% density matrices. So the even though the traversal time for the linked list is O of n and the access time for the hash map is O1, um, the matrix is basically so sparse that the ON turns into O1. So I was using 0.1% density, and imagine I have 1,000 items. The N is 1,000. But what is 0.1% of 1,000? It's 1. So that's why the numbers are basically the same. And then hashing has some more overhead to it, which slows it down a little bit more. So basically, if you're testing small matrix sizes or very low densities, the difference in theoretical complexities doesn't show up. Hashing shines when dealing with a larger number of keys. With extremely sparse data and small problem sizes, you will not you will not see a big advantage because the constant factors matter more than the complexity difference. So let's see what happens when I change from 0.1% density to 1% density. Okay, so finally, the advantages of sparse matrix with hash map have shown up. It is about 4 times faster for 900 size 900 matrices. And I was very happy to get this result because I thought all my optimization had been for nothing. But it was really just the density of the matrix that matters. Next, I decided to see if I could speed up the sparse matrix even more. And since the hash map usage is exactly the same as dict, this was a very easy change. And I made a sparse matrix using dict, Python built-in dict. So instead of hash map here, I put dict. Instead of hash map here, I put dict. And all of this code is the same because the indexing is of hash map is exactly like a dictionary. So now let's see the performance numbers for sparse matrix with dictionary. Here on this side is sparse matrix using dictionary, and on the left side is sparse matrix using hash map. So even with the exact same logic, Python's optimized dict class provides a lot of benefit, 5 times. The next thing I was curious about was what if I used, so I had just used the Python built-in dict. What if I used Python built-in list? And actually, the logic for that would be very similar to the sparse matrix with linked lists. So all I had to do was change order linked list to Python built-in list here and here. And then the rest of the logic is also the same as the sparse matrix with linked lists. And here we see the performance numbers for that. On the right is the with using Python built-in list, and on the left is using the ordered linked list class, and is about 2 times faster. So it is still slower than using even hash map, but it's the Python optimization you can see makes it 2 times faster than linked list. Here we have a chart showing all the different sparse matrices from, and on the slowest is ordered linked list. Next slowest is Python built-in list. And third slowest, this is molmat. This is actually just the normal matrix multiplication. This is using dense matrices, and it's actually faster than both of these ways. And these two are sparse matrix with hash map. My implementation is a little bit slower than instructor's implementation, but it's using the same logic. And then this line is when we switch using the same logic as HashMap, but we switch the data structure to a Python built-in dict. That leads to a lot better speeds. And then on the very bottom is NumPy speed, which is very, very impressive. And it's basically flat. So to recap, this top line order linked list uses the same logic as um, Python built-in list, but this is the list. These two are the same. This list, Python built-in list, and order linked list. These two use the same logic. It's just a different data structure. And then the hash map here and the dict, they use the same logic, but again, this is the difference between um, Python built-in classes. These two are the same. And something very interesting here is if we zoom in by a lot, you see on the left, these are the times, and these are looking at pretty small matrix sizes. We can see the overhead of hashing. So from the jump, hashing takes up more time than linked lists or anything else, but then quickly it overtakes it in performance as the matrix size gets larger. So this would be the difference right here to right here. The difference, this is the overhead. And it's why linked lists perform better at very small matrix sizes. Surprisingly, though, Python's built-in class dict does not have this overhead. And if we go back in the data, we can see exactly at what matrix size uh, hash map overtakes ordered linked list. So in the beginning, let's see, hash map is still slower. Hash map is still slower at 60, at 70, at 80, at 90, at 100, and then at 200 is when hash map overtakes order linked list. So this project was a lot of fun to do. I loved seeing the performance numbers get better and better with each optimization. And it was also really, really cool to see just how fast Python built-in classes were. And thank you for listening.